Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 8, 2025, just 2 days ago. It introduces VideoCoF, a chain of frames reasoning approach that lets a video diffusion model first decide where to edit and then apply the edit, achieving precise mask-free video editing and state-of-the-art performance on VideoCoF bench using only 50,000 video pairs. The paper is titled Unified Video Editing with Temporal Reasoner, and as we will see later, the implications for controllable, efficient video editing are quite significant. Also, the author shared a GitHub repo for hands-on use of VideoCoF. You'll find Python code for inference, setup scripts and requirements, plus example shell scripts for object removal, addition and local style transfer. There are instructions to pull the pre-trained checkpoints from Hugging Face and run single or parallel video edits. And on Hugging Face, you'll find the VideoCoF checkpoint, plus links to WAN 2.1 T2V 14 billion parameter weights, install instructions, and command line examples for object-level video edits. Figure 1 gives a teaser of what VideoCoF can actually do in practice, showing precise edits spread across space and time. The top left panels demonstrate multi-instance removal, where specific people vanish, while the rest of the scene stays intact. The top middle panels show adding new characters and objects that move naturally with the scene. The top right panels highlight local style transfer, such as recoloring a rabbit or turning tree bark into crystal. Along the bottom, the figure illustrates both long-range editing over more than 100 frames and detailed outfit changes that stay consistent as the person moves. Figure 2 contrasts how naive temporal in-context editing works versus the new chain of frames approach, which is why this method can be both precise and mask-free. The left side shows the old setup, where the model only sees source frames and directly predicts edited frames, so it often confuses which person or region to modify. The right side shows the new pipeline that first predicts a soft reasoning frame highlighting the edit area, then generates the final edited frame. Along the timeline blocks, the see, reason, and edit stages appear as different colored token segments, which makes clear that reasoning tokens guide and localize the subsequent editing tokens. Figure 3 explains how the chain of frames system actually runs an edit from end to end. The whole diagram shows source frames encoded into tokens, then passed with noisy reasoning and target tokens through the video diffusion transformer, so the model first localizes the change and then performs it. On the left, a video autoencoder turns raw frames into compact token grids. Across the center timeline, blue, orange, and green blocks represent source, reasoning, and edit tokens that the model denoises under a text prompt. On the right, the rope extrapolation panels show how special temporal position embeddings keep motion aligned while letting the model generalize to longer videos than it saw in training. Table 1 sums up how well different video editing models actually follow instructions and preserve video quality. The key message is that VideoCoF scores highest on instruction following and success ratio, so it makes the edits people ask for more reliably. The middle columns report average scores from GPT-4o, judging faithfulness and visual quality. The right columns list perceptual metrics like clip-T and dyno, which show that VideoCoF keeps both alignment and structure very strong despite using far less training data. Alright, the big takeaway is that chain of frames reasoning turns video editing into a see, reason, then edit process, giving mask-free yet precise, localized control. Longer term, this kind of explicit temporal reasoning could become a standard control layer for many video generation systems. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.